This talk is entitled Planning to Fail with Reverse Psychology, Power, Failure, Resilience for the Persistent Memory Developer. I'm Steve Heller, President of 2 Misses Corporation. Do I need power, failure, resilience? Does your program generate mission-critical data that must be consistent even in the case of power failure? Do you need to be able to resume from a power failure with the least reprocessing of previously processed data? If either of these is true, you need to make sure that your program is resilient in the face of power failure. You may wonder whether using a commercial or open source database would solve this problem for you so you wouldn't have to worry about it. Of course, SQL databases claim power fail consistency, but do they actually provide it? See the paper called Torturing Databases for Fun and Profit by Mei Zhang et al. With a link on this slide. The authors of that paper found that all databases they examined failed under simulated power faults. Alright, so you can't rely on a SQL database, but after all, this is a persistent memory conference. Surely persistent memory will solve the problem. Unfortunately, that's not true. It's a lot easier to guarantee consistency with persistent memory and still get reasonable performance. But just having persistent memory does not solve the problem for 2 reasons. First of all, current persistent memory implementations require manual flushing of data from caches before the data can be considered persistent. But even when that limitation is removed, you still need to be able to tell where you were in your program when the power went out. Interestingly enough, what we now call persistent memory is not the first type of computer internal storage that could retain its information when the power went off. When I started programming in the 1960s, DRAM had not been invented, and the typical computer memory was composed primarily of core memory. Because core memory was magnetic rather than electronic, it was natively persistent over power failures. The only part of the computer memory that was electronic was the processor registers, including accumulators, address registers, and the instruction pointer, totaling only a few hundred bytes of data. In the event of a power failure, the CPU would receive a non-maskable interrupt telling it that power was going down and that it needed to save its registers to a reserved area of the core memory. When the power came back on, the CPU would get a power on interrupt that would let it know that it had to restore the registers from the reserved area of the core memory. As soon as the instruction pointer was restored, the program would continue as if nothing had happened. So if core memory was natively persistent, why the switch to DRAM starting in the 1970s? 2 reasons: speed and cost. Core memory was built largely by hand and could be miniaturized only so far, leading to a minimum cost of about 1 cent per bit. On the other hand, semiconductor memory, including DRAM, could be reduced in size and cost as well as increased in speed almost indefinitely. This continuing increase in performance and storage capacity for DRAM drove core memory from the market during the mid-1970s. But since DRAM, unlike core memory, loses its contents when the power goes off, the only currently feasible way to make program data persistent would be to write it all out to an SSD during an impending power failure. However, due to the large capacity of DRAM, that would require a massive battery to power both the CPU and the SSD during the power failure. You might think that persistent memory would solve this problem because it doesn't lose its contents when the power goes off. But this isn't true because program data, e.g. local variables and the stack, aren't currently stored in persistent memory but in DRAM. Is this a permanent problem? Not necessarily. There are plans to create computer systems that support a standard called EADR for Enhanced Asynchronous Dynamic Refresh. Systems implementing such a standard can guarantee that data sent to persistent memory will in fact be made persistent in the event of a power failure. Not only does this make it faster and easier to guarantee persistence than with the current mechanisms, but it would then be possible to modify a compiler to store program data in persistent memory rather than in DRAM. On such a system, programs could continue after a power cycle as they did in the core memory days. However, such systems aren't here yet and may not be here for several years. Even after they are available, systems without ADR will almost certainly be around for quite some time, so we still need to worry about these issues for the foreseeable future. How do I start designing for power failure resilience? First, you have to identify all of the data necessary to enable your program to resume after a power failure. Such data includes which record you are processing, which step in processing you have achieved for that record, and the prior values of any totals or other aggregates before processing of that record began. The processing steps have to be sufficiently granular that it is clear exactly where the program was when the power went out. For example, if you need to know whether a record count has been updated, you may need an old and a new record count that should always have a fixed relationship unless the power failed at a specific point. Where was I when the lights went out? This is where the reverse psychology joke in the title comes into play as thinking backwards. To be more precise, in order to determine how to restart the program properly when the power comes back on, you have to be able to answer the following question for every line in the code. If the power goes out at this line, what data would I already need to have preserved to know the state of the program on a restart? A more basic question is, how do I know that any data is preserved? Obviously, besides solving the problem of what data needs to be preserved, you have to be sure that the chosen data is preserved. This means that any data that you have written to the persistent memory must have been flushed out of the cache, because if it is still in the cache when the power goes out, it will not actually be persisted. Fortunately, Intel's PMDK has done all the hard work of flushing via their pmem, memmove, pmemdrain, and related functions. In a properly configured system with these functions used properly, you can know that your chosen data will survive a power failure. The open source example program that will be discussed here is available at 2misses.com/example. This program has three functions. Initialize deletes the existing memory mapping file in pmem. Check validates whether the data are crash consistent. Process does the actual transaction processing. Note that you can run the program with and without resiliency so you can see the performance implications of those options, discussed later. The most interesting of these is process. This begins by mapping program variables to be protected into specific areas of the mapped pmem file. Then it calls handle processing status, which checks the current transaction count and transaction status to determine the transaction history since initialization. If the status is not in transaction, that means the program hasn't been interrupted during a transaction, so it can start processing the next transaction normally. A transaction consists of subtracting a value from the main account and adding that same value to the sub account. After those operations are finished, it commits the transaction and continues. But what if the program has been interrupted during a transaction? If that is the case, it calls continue after interrupted transaction. This first checks whether total transaction processing count is one more than old total transaction processing count, which should always be the case if we haven't been interrupted between the updates of those two variables. Assuming this is true, it then checks the current transaction status. Let's assume that is commit started. In that case, because that status is set only at the beginning of commit transaction, we know that we had started the commit transaction operation before the power outage, but hadn't yet gotten to setting the status to the next status, cleanup started. In that case, all we have to do is rerun the commit transaction operation, and we will be back in a consistent state. Now suppose that the status is cleanup started. Since this status is set only in cancel transaction and commit transaction, we can tell by looking at those functions that when this status is set, we are either about to update the old total transaction processing count, or we have already done so but have not yet gotten to updating the new total. However, we have already determined that the old and new transaction processing counts are consistent, so that must mean that we have not yet updated the old total. This means that all we have to do is to update the old and new totals, then call clear transaction status to finish up the transaction. Well, this may sound good, but does it really work? Since I've already mentioned that a lot of databases claim to be resilient against power failures but fail when tested, skepticism is definitely warranted. So rather than tell you why I think this will work, let me do a little demonstration. I'm going to start running this program on my PMEM server, then cut the power while it's still going. Then I'll restart my machine and run the program again, first with the check operation to validate that the data is still consistent, then with process to finish the job. The demonstration video is coming up next, but it's sort of hard to see the screen in the demo video even with the biggest text, so I've added a screenshot of the result as the next slide after the video. Okay, so now we get a better look at what the screen looks like after the recovery. When the power goes back on and I rerun the program, it takes up exactly where it left off. In this case, it detected that the old transaction count had been updated, but not the new transaction count, and it can detect that because they should never be the same, and in this case they were. So that's the only place in the code that that can happen, and that tells it that the next step is to update the new transaction count and then continue by finishing up the transaction, cleaning up everything that has been done during that transaction. Then we have the millions of clock ticks for processing, and then we have a message that really shouldn't be there. I added a feature to let me know if the transaction that was being processed when it stopped was actually done. We weren't actually in a transaction, and I didn't put in the conditional code for that properly. So that message there, not in transaction when interrupted, will not be there after I make that change, but I'm not going to redo the demo just for that because it doesn't mean anything. It's just an indication this is a real demo. And then finally we have something that says total value equals initial value, test passed. That's the explanation of the recovery screenshot. This sounds like a lot of work. Are there any pre-existing solutions that I can rely on? Yes, Intel's PMDK has a transactional framework that you can use rather than writing your own code for resilience. You should definitely look into whether your program fits their paradigm. If so, you should seriously consider using their solution rather than doing it yourself. In my software, described later, I'm doing all the storage allocation myself rather than relying on PMDK storage management. This gives me more flexibility in handling multiple volumes of PMEM, extending the size of individual files and the like, but it also prevents me from using the PMDK transactional framework, even if I would otherwise be able to use it. Okay, well, you may be thinking to yourself now, wow, that's pretty cool that you can turn off the power and your program still remembers where it was and you can start up from that point again. So maybe I should do this for all my applications. No, that's not a good idea. If you don't need resiliency against power failure, you should not implement it because the performance hit is likely to be extremely serious with current technology. In the case of the small example program running on Windows 10, although I didn't test the power failure in that case, 1 million transactions with resiliency turned off takes about 69 million clock ticks, so about 69 million CPU cycles for 1 million transactions. And a large percentage of that is in the performance monitoring, the thing that puts the dots out on the screen. Running the same 1 million transactions with resiliency on takes about 17 billion clock ticks. So it takes about 250 times as much time to run it with resiliency on as with resiliency off. What about real world applications? Do I have any data for that? Yes, I do. The reason I developed this approach to power fail resilience in the first place was to add it to my 2misses library, which implements a hash table for persistent memory. 2misses is described in a fair amount of detail at 2misses.com, which is the number 2, misses.com. I should note that adding resiliency to 2misses has been successful in the limited testing I've done under Ubuntu, but the same approach has failed under testing on Windows, at least partly because my server doesn't follow Intel's rules for populating persistent memory devices, as far as I've been able to determine anyway. I am arranging to acquire a new system that will be configured according to Intel specifications, and that system will be used for more extensive testing. I expect that it will work there, and if not, at least I'll be able to figure out what's going on. Okay, so how do these effects play out with my commercial application, the 2misses hash table? The test case is exactly the same as the one in the small example program discussed previously, except that the data is stored in a hash table instead of fixed locations in a PMEM file. Processing speed for 50 million operations with resilience on is about 110,000 operations per second, and with resilience off, it's about 5.8 million operations per second for about a 50 times degradation in performance. The reason this isn't quite as bad as the small example program is that both versions have to do all the other work needed to look up the records in the hash table. Summary and further directions. The main takeaways are, at present, it takes a lot of effort to provide resiliency against power failures. Use an existing solution like PMDK's transactions if you can. Right now, power fail resiliency also slows down programs dramatically. Thus, it should be done only when necessary. Eventually, EADR combined with advanced compilers that allow storage of program data on persistent memory will reduce or eliminate both of these drawbacks of providing resilience. But for the next few years at least, if you want it, you'll have to pay for it. If you do need to implement it yourself, you should